All right, let's get started. So welcome everyone. For those of you who don't know me, my name's Yonik Seeley. I'm the original creator of Solr, as well as a co-founder of Lucidworks, and I currently work at Cloudera in the search team. And I know we're up against a happy hour, so I'm going to try to go fast and get through everything here. All right, so what is Solr? I actually adapted this presentation from a Strata Hadoop world thing, so hopefully you all know what Solr is, and I can just skip that slide and we can go even faster. So here's a partial Solr architecture slide, and the green boxes are the new things that I'm going to be talking about. So it's like the parallel SQL, the streaming expressions that it's built on, and some about the JSON Facet API as well. And I threw in a little graph too. So a lot of stuff. So this is really a little bit of a sampler on the different ways you can get, so some of the simplest analytics, just some facet counts for the color field. So version 1 is, it's all query parameters, flat, nice and simple. Facet.field equals color, facet.limit equals 5. You get the top 5 colors from your search results. If you don't know what faceting is yet, I will have a slide on that later. But so the JSON Facet API, which I sort of think of as faceting version 2, it just does, same thing. We're asking, the field color, limit 5 in a JSON syntax. The streaming expressions, this isn't quite an apples to apples comparison because, we actually have the search in here as well. You can't really separate it out. But, we're doing a roll up on the color field and asking for count star. And lastly, SQL, which, probably a lot of you already know, we're asking for count star after we do a group by the color field. So first, let's start with the JSON Facet API. But even before that, a little overview of faceted search, just in case some of you don't know what it is. There's a surprising number of people in Strata Hadoop world that had no clue what faceted search was. Probably like a lot higher percentage here, but just in case, faceted search is really breaking up your search results into categories, and it's like the best is just like, to give an example, this is an Amazon search where I did a search for Android tablets, and you can see the top ranked tablets on the right hand side, and then on the left hand side you have your facets, and the facets just break the results into like display size, average customer review, and it calculates little counts. In the gray, you can see it by the total number of items that match that count. And it also allows users to usually, this is the guided navigation part, click on those links to sort of drill down into their search results. So I've started the new facet module because over time there's been a lot of functionality in Solr that's been developed that hasn't necessarily worked that well together, right? These are like sort of developed as like little discrete pieces, like statistics say, and the statistics did not work well with facets. Facets did not work well with field collapsing. Just all these little, pieces of functionality that worked fine by themselves, but just didn't really all talk to each other or had different ways of talking. So one of the goals was to provide a sort of platform so that all these different pieces of functionality could be used together. The other goal was to maintain a focus on web scale interactive performance. So basically, backing websites where you have a mass of queries coming in all the time, and you have to have low latency because it's interactive. Somebody clicks on a link and they want to see the results right away. And the other part, of course, is just the ease of use, having a unified API to access all this functionality, and that's what I call the JSON Facet API. So here is the simplest, almost like a degenerate example of the JSON Facet request and response. So we have our normal query, and we have this JSON.facet equals, and then a JSON snippet, and we're just saying, give me the average price, name it X, give you the unique number of brands, and name it Y. And so this isn't even what you'd think of as faceting. This is normally actually what you'd think of as statistics, if you know about the statistics module, or the statistics component as it's called. because we're not really breaking it up into categories or anything yet. We're just really taking all of the documents that match the query and then calculating, some statistics for that. And then on the right-hand side, you can see our simple response. We get the number of documents that fell in that facet bucket, what we call the root domain, and the X and the Y that we asked for. So the terms facet is really what we think of more as faceting. And the terms facet basically defines buckets by unique values or terms in a field. And so in this example, we define a shoes facet, and the type is terms on the shoe style field. And so this will create a facet bucket for each unique shoe style. And then we sort by X descending, and X we define later. So this is something that we can't do in Facets version 1. Facets version 1 really only calculates counts and sorts by counts. That was the whole deal of faceting in the past. It was just all about counts. And now we've just expanded it to be like, well, anything you can, statistics, any statistics that are currently supported, and we have a whole bunch. So we're sorting by X descending, and X is defined in our facet block, where we say X is the average price and Y is the unique number of brands in that facet bucket. Things in that facet block get done for each facet bucket that's created. And so on the right-hand side, our response, you can sort of see that we get back our shoes facet, and we have a bucket list. And each bucket list has the value for that field, the number of documents that fell into that bucket, and then the X and the Y. So that, the facet, the X and the Y is calculated for each facet bucket. You can also see how the structure of the response sort of matches the structure of the request, just from a nesting perspective. And that's one reason why I chose JSON as a way to express these nested facets. So now we get more complex with adding an additional subfacet. Say that we have our top level facet that we started with on the shoe styles, but we want to further break up each resulting facet bucket by colors now. And so we take our original request, and it's exactly the same, except right where we ask for our X and our Y, right after that, we define a colors facet. And so basically we're going to do this colors facet per bucket because it's nested inside that facet block. And our colors facet is a terms facet on the colors field, and we just accept the defaults for the rest of it. So by default, it calculates counts and sorts by count. And then in the response, again, the structure of the response really doesn't change from our previous example, but we just get this extra information per facet bucket. After our X and our Y that we had previously, now we have this colors facet response that has its own bucket list. And so now we can see for hiking shoes, well, we have 12 brown and 10 black. And we have a lot of facet types. The terms facet, the range facet would be good for, say, histograms when you want to break up things into date ranges. And the same thing for numeric ranges. You can break things up in salary ranges, whatever you want. Query facet, it makes a facet bucket out of the set of documents that match an arbitrary Lucene Solr query. So that could be very powerful. We can nest these things unlimited. You can have range facets under term facets, under query facets, just to any really depth that you want. We have multi-select faceting. That's where it allows you to check support for checking instead of just checking a single color that you're interested in, you can check multiple colors that you're interested in from the UI perspective. And nested document support as well. All right, so that's enough about JSON facets because we're going to move on to something really cool new feature in Solr, streaming expressions. So this is really a new generic platform for distributed computation over Solr Cloud. And it's the basis of the SQL stuff. The SQL stuff is built on top of the streaming expressions. I know the title of my talk is actually called something, parallel SQL and analytics. I actually spent a lot more time on the streaming expressions because that's where all the work has been happening. It's really optimized for, unlike a lot of distributed search before it, it's optimized to work across entire result sets. And it has this sort of MapReduce-y like shuffle during the parallelism phase, so you can really like scale things out. It sort of is reminiscent of MapReduce, except a little bit more of a real-time MapReduce. So the simplest search expression is, the simplest streaming expression is the search expression. So the search expression is just like a normal Solr distributed search. You hit, to do any search expression, you hit the stream REST endpoint, and this is enabled by default on all Solr nodes now. And so you just pass it the search expression in the EXPR argument. And so we have search. The first argument is the collection to search. Then we have like the parameters that should be familiar to you if you know Solr, the query, the field list, and how to sort the results. And then we get back our resulting tuple stream. So at this point, it really looks just like distributed search, and there's really not much of a difference. A lot of the difference is under the hood and why we call it streaming. So we call it streaming, really, and when I say streaming, this isn't quite streaming in the sense that you hear streaming out of like, Spark or Storm. We're not like streaming as much into Solr. We're not talking about that. We're really streaming out of Solr and using streaming as a computational paradigm, basically trying to compute things as they're being streamed, providing results before we've read all of the responses. So we have our worker, and that's just like whatever you hit the stream REST endpoint with the search stream, and it is fully Solr Cloud aware. So it goes out and it knows how many shards the collection is broken up into, how many replicas there are for each shard, and where they are. And so it can just go and do the search. And so the streaming expression will go and do the search for one replica for each shard and stream back the responses. But those searches are ordered such that it can really do a merge sort. And so this is where the streaming part comes in. And so the worker, it's looking at its 3 input streams. And it really just has to decide, well, which guy goes next? Which guy would sort like, first? And pick that off the input stream and put it on its like output queue. And it can just like keep doing that. And so basically, we're not really buffering anything in memory to speak of. It's really just on the order of the number of underlying streams. So you could handle 10 times the data, 100 times the data, and it may take 100 times as long to finish the computation, but it's not going to take 100 times the memory and blow up. And so that's really the essence of what we're talking about with the streaming. And if you layer this on top of other streams, then you can start computing other stuff even as the original search is still executing in Solr, because all these things can operate in parallel as they're streaming. So the search expression, there's a lot of arguments. I'm not going to go over them all. This is really just more for reference. It is notable, though, that the ZK host, it's an optional argument where you can specify the address of a different Solr Cloud cluster to search. So this search streams can go actually across clusters. So the roll-up expression is the closest thing we have to faceting. In that basically it groups by unique values in a field, and then just calculates metrics for each essentially bucket, just like faceting. The one thing to realize, though, is so it can fully execute in a streaming manner, the underlying search stream has to be sorted by what we're rolling up over. And so, like I've highlighted it in blue here, since we are rolling up over manufacturer, the underlying search streams have to have a sort by manufacturer in there. And that's just so we see all the buckets corresponding to Apple at the same time, and we don't have to like buffer everything in memory. Now the parallel tuple stream is where things get really interesting. And this is where it starts looking more like MapReduce, and this is where it really also provides the ability to really scale this stuff. So the parallel tuple stream wraps another tuple stream and parallelizes it and introduces another layer of workers in between. And so in this example, let's say we're doing a roll-up and we're parallelizing it. We've introduced 2 new intermediate worker nodes. And so the thing to know now is that each of those worker nodes is going to talk to the complete index, essentially one replica for every shard in the index. But the data is going to be partitioned, so they're only going to get half of the data back, each of them. And again, so we can correctly stream, we do something like essentially smart partitioning. If we're rolling up on the manufacturer field, then we also want to partition by the manufacturer field. And so what that will do is that all Apple buckets will get shuffled to worker 1, and all Canon buckets or IBM buckets will get shuffled to worker 2. And so these workers, it just looks like, you know, a non-distributed version, and nobody has to worry about like merging buckets later because it's just a single worker that gets all of the data for each manufacturer. And so then the worker at the end, all it has to do is as these output buckets are coming out, it just has to decide, the final worker, it just has to decide, well, which bucket comes first by my sort? You know, is it bucket A or bucket B? I guess Apple comes before Canon. So this is what the parallel streaming expression looks like. So, you know, it wraps the roll-up, which wraps the search. It's notable that the first argument that I have collection 1 here in orange, that is actually, that's not the collection you're searching, that's the collection to where to allocate these intermediate worker nodes. And so you can do this on a completely different collection or a completely different cluster if you want. This could be a collection with no data whatsoever that's just sort of dedicated to handling some of these, you know, parallel operations. It's also worth noting just how much you have to get everything just right to make it stream. So, you know, because we're doing all of this stuff by manufacturer, rolling up by manufacturer, the innermost search has to be sorted by manufacturer, the roll-up has to be by manufacturer, our partition has to be by manufacturer, and then finally the output buckets, finally at the end of it all, has to be sorted by manufacturer for everything to be streaming. And so at this point, you might start thinking, it'd be nice if we had, you know, some language, higher level language, that we could sort of say what we wanted and not exactly how to do it. And that's where the SQL comes in later. So we also have distributed joins, finally. So the inner join expression executes a merge join, again, so it's fully streaming. So as long as the underlying streams are sorted in what you're joining on, then it can just, you know, be fully streaming. You don't have to buffer everything in memory. Now, if you're doing a lot of complicated things, though, you can't always get the data sorted in the right way. If it's not sorted in the right way, we do have a sort stream. But sort stream, of course, that could be very expensive to get it, you know, just resort the whole stream in the right order. It's got to look at the whole stream before it can do that, right? So we also have things like hash joins. And the idea behind a hash join is that you're merging 2 streams. Let's take the smaller stream, and that one will read all into memory and hash it. And then we'll like stream the larger stream by it and join it on the way. And so it's sort of like half streaming at this point. So we have a lot more stream decorators that I don't have time to cover. But if you look in the Solr reference guide, it's really well written, and there's a lot of examples in there, and it covers them all very thoroughly. So if you're interested in this stuff, you know, check out the Solr ref guide. JDBC expression stream. So a very cool thing. We can, like, you know, the streaming APIs and stuff are good with like also handling data from other systems. You don't have to just do joins and just talk to Solr. So in this example, we're doing a join over a query from a Solr collection, and a JDBC query that, like, from any kind of database. And finally, onto our parallel SQL. Well, first of all, why SQL? Well, SQL really hasn't gone away. It's really useful for external integrations, tools, BI tools, things like that speak SQL. It is a higher level language that sort of says, like, what you want and not how to get there, and then you can have like cost-based query optimizers and stuff under the cover. And SQL really seems like it has made a comeback along with big data, and also just the more and more of the NoSQL stuff has turned into not only SQL. So we do have a /SQL REST endpoint by default on all Solr nodes. So you can just like execute SQL today if you're running Solr 6. And it translates SQL into these parallel streaming expressions underneath the covers. And SQL tables, table names map to Solr Cloud collection names. Oh, we're currently using the SQL parser from the Facebook Presto project. But it is in the works to switch to Apache Calcite. So here's sort of a diagram that some of you might have seen before. It's from the Solr Ref Guide again. And it just sort of lays out how you can architect a big cluster and sort of have tiers of different workers and specialize them if you want. You don't have to. This is like optional. So you could have like a tier of workers to handle your front-end SQL queries, and then a second tier, a green tier of workers, and these would be the workers allocated by the SQL tier for parallelization, these internal worker nodes. And then finally, in the blue, you have your normal Solr Cloud cluster that actually has the data. And these could be different clusters or different collections. It really doesn't matter. But so if you're doing things, say, like large hash joins, then one of the things you could do is you could scale out the number of those green worker nodes, or maybe give them more memory, or do both. If you scale out the number of worker nodes and partition it correctly, then that smaller stream that you have to keep in memory in hash to run the larger stream by it, well, that can be reduced as well if you're partitioning correctly. And so, like, if you double the number of internal worker nodes, each worker node only has to have, like, half the amount of memory state in memory. It's also interesting that you can do something that normal distributed search can't do. You can get this to use more of your compute resources for a single query. Normal distributed search is just going to query one replica per shard for a given search. But because we have these multiple worker nodes internally and partitioning your data, it's like multiple replicas of each shard can be hit. And so if you find that you're in a scenario where you're starting to get network bandwidth limited or compute limited at the leaves, well, then you can actually just like add more replicas for each shard and actually speed up individual queries. And that's not something that normal distributed search in Solr can do. So the simplest SQL example, we hit our SQL REST endpoint, and we give it the statement, select ID from tech products, and it just works. We also have some additional parameters that you can pass in addition to statement. We have num workers. And num workers is this auto-parallelization feature. If you're doing group by or distinct or something that can be auto-parallelized, then num workers is the number of, basically the parallelization factor, the number of internal workers that will be created. And you can also specify the worker collection and the cluster, worker ZK host. That's essentially the Solr Cloud cluster address of where to create these internal workers. We also fully support the where clause with full Lucene Solr query syntax. So you can just say where and then give an arbitrarily complex Lucene Solr query. And we have ordering and limiting. There's currently a bunch of caveats to this stuff, but I'm hopeful that these caveats will go away over time, so I'm not going to spend too much time on them. And here's just some other SQL examples from the ref guide of things that we currently support. So the one at the bottom is one of the more complex things we support. You know, support like this is grouping by 2 different fields, and we're filtering these groups with the having clause, you know, and we're filtering by, you know, aggregated metrics, and we're ordering by an aggregated metric, and we're also retrieving aggregated metrics at the end. So there's one important thing missing here that you don't see, and that's joins. And so while we do have the join capability at the streaming expression layer, it has not yet been hooked into the SQL parser layer. If I were to guess, I would guess maybe that might happen after we switch to Apache Calcite, which has this better like cost-based optimizer model, and a lot of other big data projects are using it as their SQL parser. So we also have a Solr JDBC driver now, and it actually works with quite a few clients. And so this is just like a DB visualizer, a screenshot of DB visualizer talking to Solr with its JDBC driver. And also this is a screenshot of Apache Zeppelin, which also just appears to work out of the box with Solr through the JDBC driver. And so Apache Zeppelin is like this web-based notebook that sort of enables it's like interactive data analysis. All right, now on to graph traversal. So graph filter. We have a graph query since Solr 6 that follows like edges that are sort of defined as on an ad hoc basis. You don't have to do anything at index time ahead of time. It's all really just defined at query time. It is not distributed, though. It is still useful if you can partition your data such that any of the edges you want to follow are all co-located in the same nodes. It can filter on each hop by an arbitrary Lucene Solr query, and you can specify a max depth, and it has cycle detection. So in this example, I've modeled Futurama characters. And for each character, I've given them an attribute called parents. And they essentially just like point to their parents by having the value matching the ID field. The ID field is just their name. And so our example graph query, FQ's graph, we're following from parents to ID, starting with Philip J. Fry. And so what this graph filter will do is select all of Fry's ancestors. So we start with Fry. We look at his parents field, and it says Yancey Fry Sr. and Mrs. Fry. And so we match those values with the ID field, and so that matches 2 more documents, and we just iterate from there. If anybody's a Futurama fan, notice that we run into a problem pretty quickly, or what could be a problem. It's a cycle because Fry is actually his own grandfather. So you look at Fry's father, and it actually names Fry himself as his father. So yeah, but that's okay because we do have cycle detection. It all just works. We don't go into an infinite loop or anything like that. Oh, it's just like a quick side note. If you do look in, like, you know, through Lucene source code or Lucene Solr source code and some of the test code, I think you'll also find some Zap Brannigan quotes in some of the test code. So graph streaming expression. I really just threw in the other graph query just as an introduction to, like, you know, the new graph streaming expressions, which I'm really excited about because they are distributed and they're fully integrated into the streaming framework. And they can compute aggregations as they're going as well. So the simplest example, we just like you know, hit the stream endpoint again. gatherNodes is the simplest graph operator we have, and you know, the first parameter is just the collection. And then we're walking from a value, and this is an email address, and we're matching that to the from field. So we're looking for documents that John Doe sent, and we're gathering the to field. So essentially, this single graph step just finds everybody that John Doe emailed. So let's look at a more complex example. So first, let's index a bunch of books in CSV format. And then let's index a bunch of book reviews into a different collection in CSV format. And then I have this great idea of how to build a recommender with graph. And so like step one is find books that I like. Step number two is find other users who rated those books highly. And then step number three is, okay, those users that like the same books I like, find other books that they rated highly that I haven't read. So those of you actually into recommenders and stuff probably recognize that this is not that good of a recommender, but it's just good for demonstration purposes. I also like, for like learning this stuff, I like really small data sets and not huge data sets, because if you get some answers from a huge data set and you really, yeah, it looks kind of right, but you really don't know, right? Because you can't calculate it yourself, and so it's very hard to figure out. So I always like start with small data sets to figure these things out. So if you look at the actual data, what we're going to get out of this, Haruka and Maria both rated books highly that I liked. But of those two, only Maria rated another book highly that I haven't read, and that is book 10. So hopefully that's what we'll get out of this little exercise. So step number one isn't really a graph operator at all. Step number one is just a search expression that finds the starting nodes. And the starting nodes are, we query for user, Yonik, and rating 5. So what books did I rate highly? And we get our tuple stream of the books that I rated highly at the bottom. Step number two is we wrap that initial search expression in a gatherNodes expression. And in gatherNodes, we say walk from book to book. And so what that does is it just like, okay, we found review records of my reviews that I rated books highly. Basically, it's almost like a self-join. It's finding all book reviews for those same books. And then we gather the user field. So we're finding users that also gave reviews for those books that I liked. But we have this FQ parameter. So we're only doing it for things that pass this filter query. And the filter query is, has to have a high rating, and has to not be me. And we also do this track traversal true. That's optional, and that just like adds the ancestors in the example here, just to tell you where you came from, but it's just optional. And so you see we actually get back the correct values of Haruka and Maria. And you see that basically what we gathered, user S, those became the values for the node field. So those are essentially now the nodes that we're on. And now step three, we wrap all of that into another gatherNodes. And this time we walk from node back to user. And so remember, the node were like two usernames, Maria and Haruka. And so basically what this is doing, it's selecting all of their reviews, all of Maria's reviews, all of Haruka's reviews. And we're gathering book. So we're gathering the books that they reviewed, but only, here's our filter query, only if they gave it a review of 4 or above. And we're asking for, now here's an aggregation, we're asking for the average rating. Now this average rating for the book is not the static average rating. This is the average of, based on our graph walk. Like it could be only like 2 people, there could be like thousands of reviews, but as a result of this graph walk, only 2 users that point to this book, and so we're asking for the average of those 2. So it's like a dynamic average. And we get back our results finally at the end, which is what we wanted, book 10. and the average rating was 5, because in this case there's only one review. If I were to do this over again, I might add a little bit more so we get like at least 2 and have like, we could also ask for count star, and that would just say, oh, how many users recommended this book. So if you wanted to see the complete traversal, we would just like repeat that whole nested mess that we had in the previous slide, and we'd add at the top level, we'd just add this parameter scatter branches comma leaves, and that just says we don't want just the end result, we want the whole, all of the whole graph traversal. And so then you see what it looks like here. We get like level 0 were the books, level 1 were the users, and then level 2 was the the final book we hit. The Solr admin guide actually has a little bit of support for streaming expressions now. So you can go and type in a streaming expression or cut and paste it, hit execute, and if you check off this with explanation, that gives you this graph that you see at the bottom. This graph is not a graph of the graph. This graph is a sort of logical layout of the streaming expression. We have a couple more graph expressions. So we have shortest path. That's where you identify a from and a to, and Solr will find like the shortest path between them. We have score nodes, which is interesting. So score nodes is sort of, it scores graph nodes, sort of like a TF-IDF inspired idea. So straight TF-IDF example, if you search for giant squid, the word squid is going to have a higher weighting because it's more rare in the corpus. It's more likely to be relevant when you find it than the word giant, which is much more common. So score nodes does sort of the same thing for concurrence. So the wiki has, the Solr ref guide that's on the wiki, it has a much more in-depth explanation. But basically, the idea is if you're trying to do shopping recommendations, you put something in your basket, then the TF factor here is, well, how often does this concur with another product? Basically, how often does it appear in another basket with that product, right? But the IDF factor sort of like weights rarer items a little bit more. So it's basically the inverse document frequency, right? It may be that like there's one product that's just so ubiquitous it just appears in all of the baskets, and so like recommending it, it's not that much. There's not that much signal there compared to something that's more rare but often appears concurred with the product you have in the basket. So we have been passing our graph streaming expressions to the stream endpoint. If we pass them instead to the graph endpoint, the same exact expression, what we get back is not our tuples, but graph ML, which is an XML representation of the final graph. And then what we can do with that is we can import it into tools like Gephi, and that can visualize it and further analyze it. And finally, just one quick slide on JSON Facet API versus streaming API. What are the differences? We have more and more ways to calculate, in some ways, some of the same things. So just try to give some pluses and minuses and where each are going. So the JSON Facet API, like I said earlier, it's a little bit more focused on the web scale interactive response. Really focused on, look, this needs to be sub-second. And not take up too many resources because we have thousands of these in parallel from all of our users. It also has a tight integration with traditional distributed search, and so it's just another search component. It works well with other search components, and so basically you can get that single request response where you get the top 10 documents that match the query. You can get grouped results, you can get full faceting, highlighting, debugging, whatever. It's like that, a whole bunch of information all at once to create your the web page or your view. And it has like block join support, nested document support. But the streaming expression, on the other hand, is really much more general purpose, much larger in scope in a way. And because really you can wrap streams within streams to do anything. It's like I only covered a small fraction of the streams that are available. There are like streams that update streams that you can take out the output from one stream and index all the documents in another Solr Cloud collection. People are doing like machine learning, logistic regression, just a lot of crazy stuff with this. And it can do whatever analytics you can do. It's really not tied to a document-centered universe. The JSON facets and facets in general, we're counting documents. We're always operating on documents in the index, right? But the streaming expressions, you might be querying like an external data source, another database, doing joins, and then calculating analytics on top of that. So in a way, it's much more powerful. Exact results is another use case. So right now in JSON facets and statistics in general, we have to estimate cardinality, right? We have like hyperlog support. But if you actually want exact cardinality, well, you sort of have to see all the values, and that's where you get into the streaming. And it has, of course, distributed joins, distributed graph, which I don't think, faceting is ever going to have. But I think it'll also continue to work more with JSON facets in the future as a way to just push down computation. When you get these big, complex things, the more we can push down into the nodes, into our smart leaves, and utilize the Lucene indexes that we have, the better off, and things will be like much faster. And we're only slightly late for beer. All right. Thank you.